This video is about something called Euler's method, which is a way to use instantaneous rates of change to estimate or approximate values on a function that you can't calculate exactly by hand. Which should sound familiar to you, because we've done it before a bunch of different times, including in yesterday's class, when we looked at a slope field, which shows the slope of a derivative at a lot of specific moments in time. And we use that to sketch graphs. So what we would have done yesterday, and I'll read the directions here, use Euler's method with dx equals 0.2 to estimate the y value when x is 0.8 for the following differential equation. We know that dy dx is 0.5 x plus y, and the slope field for that is drawn here. And we're told that when f of 0 is 0.4, so I will graph that point here, 0.4, starts right there. So here's the idea of Euler's method. It's the same as what we did yesterday with the graphic sketching functions on a slope field. If I know that the point passes through 0, 0.4, and I can figure out at that moment in time what the instantaneous rate of change is, and I can see it by looking at the graph, you can see that slope that's there. What I can do is say, all right, well, if that's the instantaneous rate of change at that moment in time, let's say I just kept going along that path for a little bit. By the time I got to point 2, I would be there. Well, at point 2, I can stop, pause, and reassess, find the new instantaneous rate of change, and it looks to me like it would be steeper, because you can tell these lines, the derivative is getting steeper. Well, actually, you don't even need to look at the lines. But if you do look at the lines, you can see the derivatives, the instantaneous rate of change, those little slopes, they're getting steeper as you go to the right. They're also getting steeper as you go up, although that's a little bit harder to see, but it's easier to see here. You can see the slope is increasing as you go up. You can tell that's going to be the case by looking at the dy dx, the differential equation, because since x and y are both positive, the bigger any one of them gets, the higher the slope will be. So, as we've moved along from here to here, our slope will have increased. So the idea behind Euler's method is if you take really small little steps, I know they're not going to be perfect, but they'll be close enough. So I take a very small little step and I pause at 0.2 and I reassess and I say, well, my slope has gotten a little bit steeper. So now I'm going to walk a slightly steeper line. I'll use this to make sure it's straight. A slightly steeper line until x is 0.4. But now my graph has gotten even steeper, so I'm going to go slightly steeper until 0.6. And now my graph has gotten slightly steeper. So this is what we did in our sketching last class when we sketched based on the slope field. Euler's method is doing the exact same thing, but numerically. So in order to do it, in order to learn what we need for Euler's method, I just want you to think about every piece that went into this graph that I just made. Starting with the initial coordinate where we started. So the first thing we start with is some x value and some y value. You need that information. Based on that information and the formula for dy dx, we were able to figure out the steepness at that moment in time. Right? When we're looking at the slope field, we use the picture. If we're doing it with Euler's method, we'll be doing it numerically. We'll calculate what dy dx is at that exact moment in time. We'll use the x and y that we started with, plug them in to find dy dx. Okay. That told me the steepness of this blue line. The next thing I needed to decide was, all right, how far along do I want to walk along that blue line? It's set in the directions, so that's what we did, to walk a step of 0.2 units to the right. That's 0.2 units. That's what we would call dx, the distance traveled to the right. So our dx here was 0.2. And based on that, actually based on those last two things, knowing the slope and the dx, we were able to figure out how far up the graph, or at least our approximation of the graph, went up in the amount of time it took to move over whatever our dx was. Well, there's a name for that amount that we went up. If the distance we moved over was dx, then the distance we move up would be called dy. And then the coordinates of our new point here, so the coordinates of this point right there, would be the old x coordinate plus however much I move to the side. And for the y value, it will be the old y coordinate plus however much I moved up. Keeping in mind that, of course, dx or dy could both be negative. So I could have a situation where I'm moving to the left or I'm moving down. That would just show up with dx and dy being negative. This thing that I last put here, this is what we can consider the new x value and the new y value. And if we are going to pause at that step, reassess, make a new slope, make a new tangent line, and start over, then that new x and new y will be the x and the y at the beginning of our new column. And then we at the new beginning of our new row. And then we can just finish out that row. And then we can go as far as we need until at some point we get to the end. So I'm not going to do all the calculations in this example, but just notice what would happen here is if we start with the coordinate they gave us at 0, 0.4, we can figure out the dy dx by plugging in 0 and 0.4 here. So 1/2 of 0.4 is 0.2. But we're only moving over to the side 0.2 units. So that will also be our dx. And so to figure out the dy, this is where you got to do a little bit of calculating, and sometimes it gets annoying with decimals. All you have to do to figure out dy is multiply dy dx times dx, the last two numbers I wrote down. Just multiply them together. Because when you multiply dy dx times dx, the dx's cancel and you're left with dy. So in this case, dy would be 0.2 times 0.2 is 0.04. So we'll have moved over 0.2 and moved up 0.04. So our new x value will be 0.2, and our new y value will be 0.44. And so that's the coordinate right there. That's not exactly what the coordinate on f of x would be, but it's our approximation based on the differential equation. Just like when we draw the curve using straight lines here, it's just an approximation. But if our points are close enough together, if we take tiny, tiny little baby steps before we reassess every time, our approximation can actually be pretty good. For those of you who watched the movie, I forget what it was called, the one about the women in NASA, the computers in NASA, Hidden Figures, that's what it's called. For those of you who watched that, there was a scene in there where one of the women, who's the one who's helping to figure out how to bring the first astronauts back into the Earth's atmosphere from space, from orbit, without like bouncing off and going off into space, she used Euler's method to do it. Okay, so the next point, and I'm only going to start this off, I'm not going to do the whole thing, but the idea is wherever we left off, wherever this point was here, 0.2, 0.44, that's going to be our next point for our next row, and then we'll start again. If you want to take a look at all these steps written out the long way, I do have this written down, kind of the process here. But the most important part I want you to think about are these columns. If you can remember to make all of these columns, Euler's method becomes very easy to do.